I'm Kathleen Sealey. I'm a faculty member in the Department of Biology in the College of Arts and Science at the University of Miami. Today, I'm going to talk about assessing the vulnerability for Caribbean small island developing states using ecological principles. And my co-authors are Ellery Lennon and Alex Nyberg. So let's get started. Small islands in the Caribbean need to see a way forward to survive the impacts of climate change while protecting their coastal tourism economy. The insular Caribbean is known for its islands, it's known for its beautiful beaches, and this is a significant component of the economy of small island developing states. Coastal systems comprise of the interacting inland areas and coastal shallow waters, including human subsystems, including housing, transport, agriculture, and commerce, and the natural systems. These coastal systems are exposed to the impacts of climate change through storms, waves, sea level rise, elevated temperatures, elevated carbon dioxide concentration, and runoff of pollution to nearshore waters. So coastal systems are exposed to global pressures, climate pressures, and local livelihood and development pressures. All small islands are interested in risk. All small island developing states in the Caribbean depend upon direct foreign investment, and thus they want their tourism development to have a manageable risk. Risk is the intersection of natural hazards, exposure, and coastal vulnerability. Vulnerability is going to be what we're talking about today. So what is coastal vulnerability? It's made up of two general categories of impacts: climate change impacts and anthropogenic impacts. So we are going to look at the combination of these two on the vulnerability of the shoreline. After hurricanes and extreme events, the damage to shorelines can be costly and irreversible, primarily with erosion, loss of shorelines, more land-based source of pollution, and destruction to natural coastal ecosystems. So integrated coastal management, in theory, looks at managing development with managing of coastal and marine resources. So in integrated coastal zone development, you want to manage the different stakeholder groups and want to manage local communities intersecting with tourism coastal development and protection of natural resources that provide services and livelihoods for coastal communities. The reality for coastal management in practice, and particularly in the Bahamian archipelago, is the development of large coastal resorts. These coastal resorts are fit a tourism model where they have lots of amenities. They're based on a business model that have a certain large number of individuals that can come and go. So how do we manage these development pressures against the climate change and global pressures on island ecosystems? We are going to look at a coastal vulnerability index that's been used on a number of different settings. And this coastal vulnerability index has four components: a component of coastal protection, coastal setbacks, the resilience of natural systems, plus the capacity of communities to respond and manage risks. We are going to modify this coastal vulnerability index and look at the application to small islands using solely ecological data which is easy to collect on island-wide scales and can be used for island-wide vulnerability mapping and disaster response planning. So we are going to look at the human-altered coastal areas, the lack of coastal setbacks in areas, over the resilience of natural systems that occur in the area, plus a community's response to manage and respond to these risks. So in this example, our capacity to respond and manage risk is assumed to be the same across the island, and this will be a fixed variable in our equation. So when we talk about coastal protection, we're going to talk about the natural systems that occur across the insular Caribbean, such as mangrove wetlands, rocky shores, or beaches. We're going to look at an island in the central Bahamas where we have developed an extensive spatial database on the distribution of natural communities and the vulnerability of this island to extreme events, such as hurricanes and flooding. So in this map, you can see both the coastal communities and the marine communities are mapped out, with the deep oranges and reds being coastal wetlands, the greens and yellows and lighter orange being offshore reefs, seagrass beds, and algal plains. When we look at coastal setbacks, there have been throughout the Caribbean standard horizontal setbacks that have been recommended by both the Caribbean Development Bank, but also the United Nations Environmental Program on how to protect property. So coastal setbacks are the horizontal distance back from the high tide line that you would place your building or property and allow a natural vegetation buffer to protect that property. This horizontal setback is varying distances depending upon if you have a high energy reef, a beach system, or a low energy beach, a rocky shore, or mangroves. So coastal geomorphology is one component of vulnerability. High cliffs and rocky shores are the least vulnerable. Low relief rocky shores are more vulnerable. Beaches with dunes are highly vulnerable, often because the dunes are removed in development and sand is removed in sand mining. And mangrove wetlands, because of their low-lying extent, are often severely vulnerable to flooding and climate change. So coastal geomorphology can be applied across the island of Great Exuma with elevation, and we can look at flood risk from storms and sea level rise. Let's take a closer look at this. We can see along areas of Great Exuma where we mapped out in black squares the houses that rocky shores, beaches, and mangroves have different vulnerability based upon their geomorphology and elevation. Mangroves and beaches, some low-lying beaches are in red as highly vulnerable, rocky shores in yellow representing less vulnerability. Okay, so once we have the geomorphology, how do we really assess these coastal setbacks? We need to look at the extent of natural vegetation. When vegetation is removed, you have the increased risk of erosion and flooding in coastal areas, and particularly flooding to property. And when sand mining occurs and you have introduction of invasive species such as casuarina, the Australian pine, this also increases erosion and flood risk. So resilience of natural system is the extent and condition of natural communities, especially wetlands and dunes along the coasts. These natural vegetation buffers are made up of drought-resistant, salt-resistant, slow-growing, hardy plants. So the native plants have evolved over time to stabilize the shoreline, process pollutants, minimize erosion. So we see on the left, native vegetation on a rocky shore, the right, native vegetation along a sandy beach. The offshore communities can also protect shorelines from wave energy. So the diversity of invertebrates offshore can reflect the robustness of reef and hard bottom communities that can protect shorelines and add to this protection from the coastal geomorphology. The capacity to respond to management risks is a function of the number of insured properties, national conservation trust funds, overall capacity to anticipate, manage, and mitigate disasters. This would be the subject of a whole nother study. We're assuming that this would be more or less even across the entire island of Great Exuma, but having priority areas and more highly vulnerable areas highlighted would help focus this capacity to respond and manage risks across islands and archipelagos. So let's look at our coastal vulnerability index as we incorporated ecological components. We're going to look at human altered shoreline area times the lack of coastal setbacks over the resilience of natural systems plus this capacity to respond. This is modified from Hay 2013. If we take the example of Georgetown, the largest settlement on the island, this is a highly developed, low relief rocky shore. So if we look at Georgetown coastal vulnerability, this is high, 1.325 for the island. And part of that is because the human altered shore, about 88% of the area has been altered. There's a large number of buildings, 127 buildings with moderate invasive species. And even though the coastal geomorphology is less risky, there is no coastal setback. The natural systems are fairly resilient, but this still gives us a vulnerable area. If we look at our past analysis in coastal ranking and vulnerability to flooding, we can see that the Georgetown area in the center with a number of different buildings that include government buildings, infrastructure, tourism, and private residences is very vulnerable because of the density of development very, very close to the shoreline. So coastal vulnerability is high if you have high alteration of natural communities, if you have natural communities that are highly fragmented, and if you have the lack of coastal setbacks and the resilience of natural systems is low. We can look at the highest vulnerability on the island, which is actually a high energy beach with a lot of development right up to the water line. So the building envelope goes to the high tide line. There's mostly a loss of native species with dominant invasive species such as Australian pine. Part of this is historically a built-in risk because the main highway on the island is built along the original dune line. So moving of the roads and infrastructure could reduce vulnerability to some of these coastal properties. Coastal vulnerability is low when you have high coastal protection with intact systems, you have coastal setbacks, you limit the number of buildings right along the coastal zone, and you depend upon the resilience of natural systems. So in here in Bahama Sound, you have a very low coastal vulnerability index. This mainly is a function of much of the vegetation is left intact. There is one building, it's a low relief rocky shore, and you have a lot of vegetation, even though you have the same liability of the main highway very close to the shoreline. So coastal vulnerability mapping can be a key component for coastal zone management and disaster response planning. This is the first step in helping people understand how they can use the natural environment to decrease their vulnerability to the future impacts of climate change. And thank you to our partners, the Coastal Ecology Lab members, the Exuma Foundation, the Government of the Bahamas, and University of the Bahamas. Thank you.
Hello everyone. This project is performance-based hybrid shoreline, enhancing the biological and ecological value of urban and coastal infrastructure along the Biscayne Bay area. Authors SEAHIVE and Sara Pezeshk from Florida International University, Department of Architecture. I, Sara Pezeshk, will be presenting this project. Our coastal lines are in significant distress due to the climate change. To protect the coastal area from climate change impact, a common and widely used technique is creating a hard infrastructure. This often entails constructing a concrete barrier along the shoreline to provide a shield from wave attack, which can cause a massive harm to the ecosystem by making coastal area more vulnerable to storm and destroying the coastal habitat. Performance-based hybrid infrastructure project is a mitigation strategy for resisting sea level rise, deforestation of mangrove trees, restoring salt marsh seagrass, reducing high sedimentation rate and water turbidity level, and decelerating depopulation of marine biodiversity. This project is also designing to offer people a unique experience to come and engage and enjoy their local environments. The project implements a sustainable strategy for creating a protective infrastructure framework that combines resilient shoreline with natural features. The aim is to create a performance-oriented landscape responsive to climatic conditions like water and wind forces generated over time. Performance-oriented architecture attempts to fully overcome the distinction between forms and function in design, said by Hansel. The described project consists of a smaller module called biotile, which can be arranged and generated based on macroclimatic information and data. In addition to protecting coastal erosion, the biotile will collect sediment accumulation, decrease the surface temperature, and filter the stormwater runoff. The project used environmental and climatic data for the development of the data-driven landscape infrastructure. The design methodology used to develop performance-based hybrid infrastructure is in 3 stages simulation. First, the macro level that enable the manipulation of the overall topography along the shore. Second, it's macro level that includes the creation and configuration of biotiles. And third, the nano level involving material property of surface manipulation in all 4 forms of biotiles. The evaluation process is based on the evolutionary and multi-objective optimization process, utilizing an evolutionary and analytical engine, a Rhino plugin called Wahoo. The workflow begins by formulating the design problem, followed by evolutionary algorithm. Once results are achieved and evaluated, the fittest design is chosen. The first simulation at the macro level controls the landscape to create artificial topography. The initial step is to analyze the current site slope and study the water flow to identify the catchment areas. The topographical data from LiDAR point cloud is translated to a 3D modeling format and analyzed further. The design is based on the water current and wave motion that is combining both horizontal and vertical water movement. Water currents are constant, predictable, directional movement of ocean water powered by gravity, wind, and water density. The algorithm used here is based on a sine wave equation consisting of amplitude, frequency, and cycle of or pi. The range of wave frequency within data is collected from USGS water level and coastal change forecast of the project location. There are various artificially manipulated topographies is produced from this generative workflow, which are evaluated and then selected. The second simulation at the macro level is used to generate and arrange biotile based on multi-objective parameters such as microclimatic information and data. The morphological structure that is generated through the algorithm of biotile is formulated on a biomimicry principle. The pattern generation is through an algorithmic process using the underlying code inspired by the natural phenomena of rock formation along the coastline, similar to the giant causeway on the northeast coast of Northern Ireland. This natural phenomena of basalt formation generate a polygon pattern called the Voronoi configuration during an intensive volcanic eruption. The Voronoi algorithm reflects efficiency in nature, since the arrangement of the space is dependent on the proximity of the neighboring cell. This provides an opportunity to design a surface area that is self-organized to the site and is adaptive to the environment parameters. Height differentiation in biotiles is coded based on the solar radiation data from the site to optimize shading on the adjacent tiles. This process is also simulated through an evolutionary and optimization engine that produces multi-generation configuration. The biotile ranges indicates inside each color-coded zone are estimated from the storm surge depth data obtained from the storm surge simulator from Category 3 hurricane. The zoning criteria are also designating an area along the water for the third typology called the rock pool that collects sediment during the storm surge and other extreme events. This optimization is based on a scientific case studies experiment for sediment accumulation strategies. The tile's height and the degree of inclination is informed and generated by the algorithmic code fed by the local pool water data, which indicates the turbidity level. These processes result in 4 tiles typology. First, a solid typology that withstands water and wind, as a result, slowing down the erosion at the same time, filtering and managing stormwater runoff. Second, a donut-shaped typology with the pot in the center of the tile to house seeds for mangrove restoration. Third, an artificial rock pool typology positioned to collect sediment runoff. And lastly, a porous typology that retains and restores seagrasses. At the same time, by using eco-friendly materials and mimicking natural texture deformation, all of these tiles promote biodiversity. The third simulation is at the nano level, which focuses on the biotile materiality and surface texture. The surface deformations are developed based on a precedent study called Eco-Engineering Urban Infrastructure for Marine and Coastal Biodiversity, which intervention have the greatest ecological benefit. That compares the effectiveness of eco-engineering methods to improve biodiversity. Various forms of intervention are introduced and tested to reflect various species efficiency. Different surface manipulation techniques have been used in the tile to increase the abundance of intertidal flora and fauna by the increasing texture, crevices, and holes. We have also prioritized the selection of biotile materials to minimize marine life's impact and improve its robustness and sustainability. During the testing process, several combinations of material were used to explore and examine their capacity and limitation. In particular, the tests help us to better understand the eco-friendly concrete property as a potential material with the production process that produces fewer greenhouse gas emission than standard cement. The structural performance of the tiles was assessed before their placement near water. The analysis was done with the computation of fluid and dynamic analysis to test the proposed intervention under wave and wind impact forces. The evaluation result of the various CFD simulation led to decision to perform finding and fabrication method. During the project development, several prototypes were produced for testing. The fabrication process is part of the design requirements from the outlet in this workflow. The prototypes result in a composition of 4 main topology produced with either additive and subtractive manufacturing method. To test the biotile performance, we have placed and are monitoring the prototypes along the shoreline to evaluate their impacts on the erosion of marine fauna. The donut-shaped tile configuration will evaluate it based on the planted mangrove seeds, health, and alternation in the shoreline biodiversity. The rock pool configuration will be evaluated by measuring the amount of sediment accumulation in the biotile center. The composition will be evaluated for its performance against wind, water forces, and their overall effect on the existing ecosystem. Our results will be compared with a set of standard tiles, which will have also placed in close proximity to provide comparison base. We realized after the first trial that the internal structure infill that supported the outer wall was not performing as anticipated. As a result, we have developed a uniform system in which the structure serves as both a wall skin simultaneously using the reaction diffusion algorithm. This study aims to evaluate the possibility of algorithmic workflow for resilient design and test a performative infrastructure that can contribute to environment biodiversity. If these trials are successful, our goal is to expand and apply this methodology to other ecosystems in need for protection and restoration. This goal can be only achieved if there is a higher level of collaboration between disciplines and practitioners. In addition, we are hoping to help policymakers who manage environmental crises to implement effective policy that promote environmental research. Thank you. The project has been a collaboration between architecture faculty at Florida International University and the Center for Aquatic Chemistry and Environment, CREST, an NSF-supported center at FIU International University.
So, Sara, thank you very much for that presentation. I had no sense of the sophistication of those biotiles and the amount of modeling that goes into the design of them. So thank you very much for that presentation. That was excellent. Again, I want to remind our audience and even our panelists, encourage you to put any questions that you might have into the Q&A box at the bottom of your screen. And we'll, of course, address them when we get to the panel discussion portion of our session. The last talk of our session is from Landolf. And Landolf's presentation is entitled Structural Morphogenesis of an Eco-Friendly Marine and Estuarine Protection System, the SEAHIVE Paradigm. I will queue up Landolf's presentation now.
Hello everyone, my name is Landolf Rhode-Barbarigos. I'm an assistant professor at the College of Engineering at the Department of Civil, Architectural and Environmental Engineering. Today I will present you our work on the structural morphogenesis of an eco-friendly marine and estuarine protection system, the SEAHIVE paradigm. This work is based on the thesis of my PhD student Mohammed Ghesian, collaboration with Dr. Brian House from Ocean Sciences and Director of the Sustain Facility, as well as Drs. Nani, Suraneni, and Andiroglu, also from the Department of Civil, Architectural, and Environmental Engineering. Let's discuss a little bit the context of this presentation. First, let's talk about the disasters. According to the National Center for Environmental Information, the United States have sustained 273 weather and climate disasters since 1980. The total damages and costs exceed 1.7 trillion. Those events include 45 tropical cyclones. In the last 10 years, tropical cyclones and hurricanes are responsible for more than 53% of the total damages and more than 6,500 deaths. The mapping that you can see here of these disasters clearly identifies southeastern United States, home to over 70 million people and over 20,000 miles of coastline, as one of the most accessible areas to such disaster. Nevertheless, the coastal population in the United States as a whole and in our region has not ceased to increase, with some actually of the most valuable properties being in those areas. Therefore, it is critical to make coastal communities more resilient and resistant. When we talk about resilience, when it comes to the built environment and the infrastructure, resilience is associated to the ability to deliver a certain level of service even after the occurrence of a disaster, and to recover to the desired functionality level within a given time period. A resilient built environment and infrastructure is thus more resistant to weather and climate disasters, limiting their physical impact. To increase the resistance to tropical storms and hurricanes, there is a variety of solutions, from soft green engineering solutions, such as the living shorelines, to hard gray designs, such as seawalls and revetments. Here you have a variety of solutions coming from the Back Bay study. Now, seawalls and revetments are often considered as the most reliable solution, especially for areas where we have a small footprint availability, harsh wave conditions, and high surges. However, existing design systems, existing seawall systems, do not always perform to the desired level, while they typically support lower biodiversity and fewer organisms than natural shorelines. So we can seek to find improvements over the traditional systems in performance as well as in biodiversity by green engineering solutions. And this is what we're after here. Actually, to come up with a solution for a more efficient and eco-friendly shoreline protection system, in this work, we employed the concept of structural morphology. This framework studies the relationship between a structure, its form, the material and forces, and morphogenesis here refers to the process that distributes the materials partially within the system. For the structural morphogenesis of an eco-friendly marine and estuarine protection system, biocompatibility is the key, as it has to be considered within all aspects of the structure and be compatible with the organisms of the local ecosystem. So the product of our research is called SEAHIVE. It is an engineered shoreline protection system that is composed of concrete perforated hexagonal prism. It's a modular system. It is made out of concrete with non-corrosive reinforcements, and its modularity provides a regular hexagonal tessellation that can be used vertically or horizontally. The perforations that we have on the side face of the elements provide passage for the water to flow under surging or breaking waves, dissipating the wave energy within the elements, while they add also structural complexity to the structure, which improves their potential for biocompatibility. In our case, the morphogenesis of the SEAHIVE shoreline protection system has been on the physical testing has been based on physical testing in the University of Miami Surge Structure Atmosphere Interaction Facility, also known as SUSTAIN. SUSTAIN is a wind wave tank, unique because of its size, but also because we can generate directionally varying waves using a 12-paddle system combined with direct wind forces, simulating hurricane conditions up to Category 5 on the Saffir-Simpson scale. Here you have a video of SUSTAIN in action. What you see there are the mechanically generated waves, and you can also see that there's the wind there. So the wind amplifies their effect, simulating exactly what happens in a real storm. So we have winds mechanically driven, but also amplified by the effect of the wind. So in our first phase of the testing, what we did is we tested solitary SEAHIVE elements with different cross-sections and perforations under different conditions of wave and wind. So through a series of measurements, we quantified the loads applied on the different elements, as well as their performance related to wave transmission. So here you can see different elements with different curves representing basically the different pressure that is being applied. In the second phase of the experiment, the testing focused on the system behavior. Here we consider horizontal and vertical system configurations only with hexagonal elements. Similar to the first phase, different perforation configurations were tested. The perforation configuration procedure included a fully solid system, a semi-perforated system, and a fully perforated system. Here you can see a video where there is the system testing. So you have the semi-perforated configuration under testing. The model here is composed of 3 rows of SEAHIVE elements. The first row is submerged and has large perforations. The intermediate row has smaller perforations and is partially underwater, while the last row is extends above the water, has no perforation, simulating a little bit a seawall or a revetment application. Again, here we have, through a series of measurements, the loads applied on the system, as well as its performance expressed through the wave reflection, were defined. So here, what we do is we quantify the system loads, behavior, so the design, and we link that to auxiliary studies that are happening around the SEAHIVE concept. So in addition to the physical testing, we have been collaborating with other researchers on related aspects, such as material biocompatibility. Here you have a series of small tiles that we're fabricating using different cementitious materials and exposed to the marine environment for different periods, and are currently under evaluation for the biophilic behavior. For biocompatibility, field studies are critical because you have to do those studies out on the sea and capture the real, let's say, the real recruitment of those materials. But field deployments are also critical for validation purposes as well as for technology transfer. We have thus engaged with local communities for a series of pilot installations. This is our first installation. It's going to be in North Bay Village in collaboration with local stakeholders there, where SEAHIVEs will be installed as a replacement to Riprap in front of a newly constructed seawall. Our second pilot installation is an artificial coral reef structure. This installation will take place offshore of North Beach Oceanside Park in collaboration with the City of Miami Beach in the context of a Laboratory for Integrative Knowledge U-Link project, which investigates coral reefs for shoreline protection. Our third installation will take place in front of a newly developed community park in Pompano Beach called Wahoo Bay, and it is in collaboration with a nonprofit organization, the City and Broward County. This installation is a seawall mangrove planter combination. All 3 installations will be monitored and analyzed to assess their as-built performance. The structures are currently under permitting review, and we cannot wait to get the green light, as this will take our research to the next level, combining the actual laboratory results with data from those structures will really enhance our work and provide us the necessary proof that our system works so that we can take this product out to the communities for its use. Thank you for your attention. And here I would like to acknowledge the different agencies as well as the local partners and stakeholders that we have, and my colleagues who have been working with us around this project. Thank you.
Thank you, Landolf. That was excellent. Definitely hope you guys get approval, permitting to begin deployment. Very exciting. So the next portion of our session is the panel discussion. So Jen, I think we need to make sure all of our panelists can turn their cameras on. So if we could ask all our panelists to try, and let's see if we're able to get our cameras on.
No, I can't turn it on yet.
Okay, so Jen will needs to do something to give you permission, I think. All right, Jen, are you able to do that, or do I need to do that?
I think you might need to, because I'm no longer the host. I think you're
Okay,
the host.
so Sarah's in, Landolf is in. So let's see,
Sara.
Kathleen is on. Good. All right. Success.
Good.
Yes, we got it. Thank you. Wonderful. Okay. So I'm sure we'll have a number of questions, but first I want to take the chair's prerogative of asking a couple of questions. And I'm just going to, try to open the conversation, sequentially. But please encourage you all to go ahead and submit your questions. So Kathleen, in your presentation, you make a fairly big distinction between, dunes versus mangroves in terms of vulnerability. In fact, the dunes was extremely high vulnerability and the mangroves was high vulnerability, is my recollection, or something like that. But I was just wondering, was that because it was assumed that there were human interventions that diminished the efficiency of those natural environments from protecting the coastline, or just so easy for humans to be involved in that? In other words, could dunes and mangroves be just as good as something else?
Well, those coastal geomorphologies were basically based on what you would think the climate impacts would be on those intact systems. So mangroves are the most vulnerable to climate change because they have a very limited capacity to keep up with sea level rise and storms. In fact, we see a good example of that in the Florida Keys after Hurricane Irma, where a lot of older trees were killed in the hurricane, and the mangrove islands are actually eroding away. So the combination of severe storms and sea level rise is the greatest threat to even to intact mangrove systems. Secondly, would be dunes and beaches, and especially high and low energy beaches. And one of the reasons is that for dunes to recover after a storm, you have rather slow growing plants. So there are some studies that say with increased storm frequency, you can actually accelerate beach erosion. In the Bahamas, beaches are usually accreting environments because of the formation of oolites and carbonate sediments, but repeated storms can actually cause the collapse of the dunes, or maybe flooding through the primary dune to a interdunal wetland. You see the creation of marine ponds, or saltwater ponds behind the dunes after a storm. So that's why, mangroves are the most vulnerable. Intact dunes and beaches can be the second. And then the rocky shores are actually more resilient to sea level rise, especially high cliffs, of course.
Sure.
Oh,
sure.
That's why. So those are the natural systems and the impact of climate change, which would include increased storm frequency and sea level rise.
Okay. So the view is a little bit long-term, sort of the relatively long-term future of what happens to those natural systems, coastal systems, geomorphology, if you will. Okay, good. I understand that better. The other thing I wanted to ask you about, Kathleen, was I had this sense that one of the big challenges you have is quantifying things that are not easily quantifiable, right? So we're trying to put things into a mathematical formula that are a little bit vague. And I'm just wondering, how how do you validate, you know, I'm a numbers guy, so how do you validate that these numbers that we're putting, these, you know, conceptual ideas that we're quantifying are actually being quantified correctly? How do we assess that?
Well, we spent probably about 15 years trying to develop a standard coastal transects in capturing, you know, coastal plant diversity and then nearshore marine diversity. And that was greatly facilitated by the rapid ability to standardize natural communities. So, you know, now we have a federal standard on the classification of marine and estuarine communities. So that's developed a whole common vocabulary. So now we know if we have a, you know, a submerged aquatic vegetation bed, we can go in and we can have a sort of a standard assessment of diversity in that type of community. So yeah, I think the numbers are extremely important because you need a way to go back and again and again and assess this diversity in a standard way and begin to use those numbers to actually kind of quantify this whole coast. You know, what do the numbers say about the vulnerability of this site versus this site? You know, everybody makes assumptions, but it's better, like you say, it's better to have numbers down on paper. And then,
Sure. And then, you know, Sara, following on that, you know, your approach to the problem, you're devising these man-made structures that are blending the man-made and the biostructures. That approach is extremely quantitative. You're using computational fluid dynamics codes to design these structures. And I'm just sort of wondering, when you start thinking about designing those structures, do you feel like anything is unaccounted for, natural phenomena that's unaccounted for? So, you know, at one point, maybe you design them for the chronic problem of sea level rise and you ignore the storm surge side. And on the other side, maybe you're focusing on the storm surge side, but you ignore the chronic sea level rise problem. Are these holistic? You're trying to capture every possibility. Anything missing?
Yes, actually, of course, it's a challenging study because there's so much things that it's causing all of this issue, and it's hard to kind of focus on all of them at the same time. I mean, even though it's just it's kind of like you need a massive like a kind of contribution between a lot of disciplines, I would say. Marine scientists, engineers, and this is like, and you need to like kind of have them all in the same place to kind of knowing what are the issues. Every day I'm learning and I see, oh, this is a new issue. I learned today from other audience, other presenters, a lot of things that I never look into. And I'm sure there are a lot of things that, we are trying to do our best, but the best way, it's as Landolf mentioning, it's putting the actual things in the situation and absorbing it over time. And a lot of things are predictions. So things we still don't know, and we don't know the level of the sea level rise rate, and are we going to be able to control some of these? So these are like all, some solution that we are hoping, as a kind of, to me, I would see it as a somehow making people more aware about the situation and trying to look in, small picture, just introducing some of these problems.
Sure. So Landolf, we have a specific question from Katie Hagerman. What's the advantage of the hexagonal structure over a traditional riprap boulders?
Well, I was just answering to Katie on the chat that the SEAHIVE, the hexagonal there, is more versatile than the traditional boulders. in the sense that basically we have that interlocking ability, which we can sustain larger forces. Eventually, you can tune them to be hollow or not. So there you can play with basically the weight for stability, the mechanical tessellation, and the properties to sustain more wave action. And of course, like if you actually do it the right way with the different, let's say, materials that you employ, you can actually use attractants and actually enhance or allow the ecosystem to form within and around the structure, something that typically with boulder is not so successful.
Okay. So I did also have a specific question. How do you, what do you go back and measure when you deploy, and this is for Sara too, of course, you deploy these tests, you know, you have some prototypes, you put them on the coastline. What do you measure when you know, it looked like Landolf, yours was pretty sizable structure, so you're really thinking about, you know, wave wind action and how much you dissipate that. What are you actually measuring? And Sara, same for you. Let's let Landolf go first, but then Sara, what's actually being measured once we'll come to you after Landolf.
So I think the idea there for us is that you have measurements on both sides, both the ecological and the engineering side. So you have to measure growth, basically biodiversity that is developing on your structure, inside your structure. You do fish surveys, you can see how basically your structure has affected the local ecosystem there. So you have to have like a baseline from before. Same thing goes with sediment transportation. You need to actually see what will be your impact. The other thing on the engineering side will be basically wave action, how you absorb it. So you have to weigh, you do water level measurements, you do flow measurements, there current measurements to see how you affect turbulence locally. And by that, you can talk about reflection and transmission. And then you can relate that to protective features of your system. So what we have in the lab is that we control all the parameters, but when you actually deploy it, there are parameters that you do not control. So then we need to see the performance in the live stage in a way where things are basically installed in a non-perfect environment where you do not control everything. So that's the important there. So you have to be robust in a way to make it work out there.
Sure. There's a possibility of unintended consequences that also have to be
exactly. So that's the other thing. That's why you have also to start small and build up in terms of the pilot installations, so that you can measure and see also the things that we, as Sara was saying before, things that we never thought about, and there might be secondary effects that we realize there.
So sure, understand. So Sara, the installations that you seem to show were pretty. Quite a bit smaller in terms of their footprint than the ones that Landolf was. So what are you measuring there? You're not really focusing on the wind wave part. You're focusing on the biology part. What are you actually measuring there?
I mean, if you remember, I kind of like introducing a few different type of tiles. Mm-hmm. That hoping that they can also kind of promote biodiversity, bringing back some of the flora fauna that are destroying by typical Riprap structure that we have right now. Hoping with kind of using geometry and creating texture, and also using a more eco-friendly material. We can kind of bring back some of these species along the coastal line. That's actually the intention.
Sure. So Kathleen, if you were working closely with Landolf and Sara, and you wanted to sort of figure out how you would advise the small islands about what kind of artificial, biotiles or the SEAHIVE that what would you be doing? What's holding us up from actually doing some of these things? And what would you be advising them that they need to test in order to convince the Bahamian government that they should make a big investment in this technology?
Well, I think that's a good question. I think it's, we look at it one way in Miami, which is a highly altered landscape. But, I think we would have a better opportunity of applying these types of technologies in a place like the Bahamas. And what I would say is what we should do is replicate the existing geomorphology. Like I always say, you're not going to make a rocky shore into a beach, and you know, it's not good to put a hard structure, you know, in soft sediment. So I would say there's a lot of applications to replicate natural coastal processes. So using the SEAHIVE ideas in front of low relief rocky shores, or using other structures that can help rebuild a dune. I know people have tried things like geotubes that don't really work, but I think that's going to be an engineering challenge because the native plants grow very slowly. And in many places in the Bahamas, like in Abaco and in New Providence, when there is a hurricane, they'll get out at the low tide, they'll bulldoze the sand back up, and they'll replant sea oats that are grown in Florida. You know, there's a big company, Valley Crest Landscapers, and they sell literally hundreds of thousands of sea oats to the Bahamas to restore dunes. But even those planted sea oats need time, and we need to begin to try to duplicate these natural geomorphologies and then help recover and build these coastal setbacks back along natural designs. I think the big mistake is that people try to fortify a shoreline that's more dynamic, like a beach that need to move, a low energy or high energy beach, or a mangrove. So we need to look at these hybrid structures that will mimic natural geomorphologies, particularly in areas where the underlying geomorphology is a little more evident than like in downtown Miami.
Mm-hmm. So, you know, I wonder, I sort of wonder, why aren't we moving faster with some of these hybrid artificial, biological, structural solutions to some of the, you know, sea level rise and storm surge challenges? Is there, you know, is cost a big element? Are these very expensive? Is there a culturalization problem? Are people going to resist this kind of solution? What are the, you know, why, you know, we move pretty fast at building up the coastline, right? We're not, we're not holding back there. So I'm just wondering, why are we, I have this sense that we're holding back and then deploying this technology. Why is that?
I think one big reason is who's going to pay for it. You know, I think the private landowner wants to, they're just thinking, this is my land up to this high tide line, and I'm going to do my thing with it, not understanding it's, of course, it's well known in areas like North Carolina and New Jersey that, you know, you have to treat the dune and the shoreline as a continuous unit. And I think that it is, you know, this convergence of issues, you know, in property rights and who's gonna fund it. I don't think that people are fully grasping the accelerated rate. And Ben, you know this, we could have, you know, sea level rise is not going to be linear. We could have a jump, and we could have, you know, we could have a lot of bigger hurricanes like Dorian. So I don't think people are really grasping the extent of it. I think that's really my fear, is that, you know, these repeated events before we even, I mean, Miami-Dade County is trying to take a very aggressive plan on an already developed line, but it's hard to get the seed money to do demonstration projects in the Bahamas. We do have a program under UNEP, the Eco-Hydrology project, which allows us to do some demonstration projects in sort of coastal processes, what we would call, you know, coastal functionality, but it's not really on the scale that we really need to be addressing it.
Sure. So Landolf and Sara, of course, who's paying attention to this technology that you're developing? I mean, do you have people paying attention to this work that are the kind of people that are going to make those investments and going to push reforms in how the coastlines are managed in order to deploy these systems? Who's paying attention? Are they paying attention to this work? Landolf.
I'll let you go first. I'll come after.
Sara, go ahead.
I mean, for me, it's too early to say because I'm recently starting this, but I can see our people are very interested to kind of using nature-based system to deal with these issues, because we've seen how hard infrastructure it's been performing in the past decades, causing a lot of issues. So, and when I saw a previous presentation, I saw that Miami is also like trying to introduce, try to give actually permission for allowing living shoreline, which I think we didn't have that before, which I think that these are a good move. And I think we need a faster to, I think, look at these problems.
Landolf, do you have some thoughts there?
Yes. So, and first I want to come back to your question there. Like, I think that the first thing we need to talk about the timeline there. I think some of these, I would say, nature-based solutions and the green-gray are hard to quantify in terms of performance, right? So we recently started to quantify the ecological services, including shoreline protection there. And that goes from the reefs to the mangroves, and there are engineering studies that try to quantify this. But again, I think what we're missing is the pilot studies on the field. Like USGS has been making measurements there along the reefs based on the mangrove forests there. So we need those data sets to really understand, because if somebody were to implement this, they ask, how much do I need to get that level of performance? That's the first question we're asked. And if you cannot answer this, then how are you going to say, okay, well, then you can invest on this? That's the first question that I see. So it's a money question, but it's also the engineering side has to come back with the right type of, let's say, answers and solutions. So, and of course, I don't think there's one solution. I mean, we have to work on multiple fronts there. It could be dunes, it could be mangroves, it could be reefs, it could be green gray. I mean, everything there has to be in our portfolio. There's no perfect solution there.
Sure, and Kathleen raised the urgency question, that people aren't appreciating the urgency of the situation, that sea level rise is not, is non-linear, and we're seeing hints of, more powerful storms and maybe slower moving storms, slower forward speed. That, means more storm surge, and that, with sea level rise can lead to a lot more stress along the coast. So when you start to think about designing these systems, how far out into the future are you trying to design the system to be viable? Are you thinking, in terms of, how many feet of sea level rise? Are you thinking out to 2100, or are we thinking out to 2050? What's the lifetime of these systems, and what kind of planning horizon do they apply to?
Well, typically you will think about 50 to 100 year service life there. But of course, that the predictions there might be wrong. That's the key there. So you need something which can be in a way flexible. That's why the modular approach for us is key. So if something, then you can always consider changing or adapting, or even having sediments being inside, or even having limestone being filled, and so on. So you need some flexibility there, because of course the predictions that we have right now, I mean, you are the expert there, are not, written in, they're not, we're questioning our own predictions there. So
sure.
I mean, I would argue that this is more like a question that I would pose to you, and then based on your answer, I would design the system. But again, that's the challenge of today. However, I see more people paying attention to this. Communities are basically becoming more sensitive to this. Like, we have people are asking about what is it, how it works, why it works. Can we test it? Can we implement it? What are other solutions? Do you know other partners, and so on? So I think there is a movement there. So what we need to do is basically conserve that movement and guide it to the right way. So Kathleen actually mentioned, there might be ways that we can do that all together. So identifying the right location with the right modeling, with the right testing, and proposing solutions that mimic the natural geomorphology could be one way. There are other ways, I mean, other locations where we already kind of, how can I say this? We transform too much the natural geomorphology. So we have to live with that, and we have to protect our, I would say, valuable real estate. And there I mean, nature-based solutions take time. So we have to kind of bring the gray in, but in a smart way. So the gray will provide the first level of defense immediately, and then we allow the ecosystem to develop around it, if that's possible.
Sure, sure. Excellent point. If you know, Miami-Dade County, you know, Katie Hagerman is on the call here, so she can correct us if we totally blow it. But if Katie and Jim Murley came to you and said, you know, all right, Landolf, let's start talking about how to deploy this, to just scope that out. Suppose you're gonna, protect, say, a couple of kilometers of coastline on Miami Beach or something like that. I don't know where, but how would you even start to think about the costs of that? What that would mean in terms of cost structure, and how would you say, answer Jim and Katie? Is it even possible to talk about doing this next year? Is it even feasible? Is that can you do that? Can you have that conversation?
If we're talking about the infrastructure level cost, I think that if you take some, I mean, we know that the proposal there for the storm surge of the 10-foot high seawall there, I mean, that is an extreme scenario there. But I think we can have that discussion and cost that and make it relative to what we're protecting and what are the investments there, and kind of like make it so that it becomes cost effective at various stages. So of course, you're not going to do it in 1 year and that's it, and we did the construction. You have to kind of pace it out to a number of years, like all the big infrastructure projects. So then you have that investment there. And I think that if we do that on multiple fronts, then yes, we can do it. Like I would avoid having all my eggs in one basket in a way.
Mm-hmm. So Kathleen, go ahead, Kathleen. I'm sorry, you were about to speak.
I would just say life is not going to continue on as we know it, over the next 10 years, really. So we have to pick our battles. And what is it that we're actually trying to accomplish? Are we trying to improve nearshore water quality? And, as Sara presented, some very interesting designs to increase maybe the nutrient and runoff processing in these elaborate coastal structures. Are we trying to stabilize the shoreline? Because stability in itself is of value to the nearshore ecology. We almost certainly are not going to prevent flooding everywhere. So you have to pick the battle. What is the battle you're going to fight? We are not going to live in Miami on into the future as we have lived, previously. So then that's true in any place, a coastal area. So I think it's important for people to pick their battle. Are we going to stabilize the shoreline? Are we going to try to improve nearshore ecology and water quality, which is an important part of the quality of life living on a coast? Are we going to try to stabilize so we don't have coastal erosion? So, there's a lot of things I don't think you're going to have a silver bullet that will solve.
Sure. And Kathleen, are they having that conversation? I mean, to me, that sounds like maybe not a generational conversation, but a conversation that, requires community input, takes some time. Are they having those conversations in the Bahamas?
Oh, yeah, I think they are. I think it's, especially after Hurricane Dorian, there's things are dramatically changing, and a lot of infrastructure topics, which, I'm sure other people have talked about. People are talking about redesigning. The Bahamas already has a very strict building code for residents. Almost everything is constructed out of cinder block. Most Bahamian settlements traditionally were on higher ground, because there wasn't air conditioning and there was more breeze. So I think people are really looking at this whole infrastructure cost, and that initiated our beginning doing some flood mapping to look at, you know, how many kilometers of roads on each island are vulnerable to flooding, which, you know, when the roads flood, you can't have emergency response, or, you know, we saw that in Abaco. So people are looking at smart ways, realizing there's not a lot of, you know, there's not going to be unlimited funds. How can they be more resilient? Funding agencies like coming in, like the Caribbean Development Bank and the Inter-American Development Bank, have this huge blue economy initiative. And there is going to be, it's probably going to be easier for the Bahamas than for the US or for Caribbean countries, because they're going to be forced to have certain guidelines for funding infrastructure, whereas the US maybe not have that force, because the you know, the outside funding agencies are going to require that.
Yeah, I believe at least Miami-Dade County, I know their resilience officers and folks are trying to start having those conversations about what's important to the community in order to protect. But this is tough stuff. This is really tough stuff. But, you know, getting the community buy-in to figure out exactly where we want to invest, what we're going to return to its natural environment, and what we're going to protect is a very difficult problem. I see that as almost generational. That's tricky stuff. Any last thoughts from our panelists? Comments, questions? Sara, anything you want to add? Landolf? Kathleen?
Well, I just want to give the other perspective there, because so I had the chance to visit Abaco and interact with basically the government there. And one thing that struck me is that there's the social perspective also. Like we were talking about the quality of construction, and when there are people that cannot afford a good quality of construction, then the difference on the performance of their, let's say, structures is so much different. So it happened to me that I was on a street, and on one side you had a nice structure, almost intact from the storm, and on the other side it's that famous structure which was upside down completely, the building. So that's where I want to say also, like from a manager perspective, it's very hard how you actually impose or how you actually guide, let's say, the community towards those discussions and basically to take over and provide guidance there.
Okay, thank you. So just allow me to thank Kathleen, Landolf, and Sara for really excellent presentations and a fabulous discussion. It's my responsibility to make sure I remind you all, sharing on my screen here, the next session that starts in about 15 minutes, I believe. The upcoming session looks to me like we have 5 presentations: physical resilience, building on real estate industries, economic resilience, urban policies, social, economic, and physical resilience, academic research partnerships, physical resilience, green, blue, and gray lines of defense, social resilience, climate migration. So that looks like a very vigorous session, and I want to encourage you all to attend. And again, I want to thank our panelists and their presentations. They really were thought-provoking. And I hope Landolf and Sara can continue to do the real-world deployments. And I'm really excited to see Kathleen continue to assess the risks and help the Bahamian government respond to those risks. So thank you all very much. It was really an excellent session. So thank you.
Thank you.
Thank you. Thank you for having us.